Hi, my name is Rick Langer, and I'm your host for iFlips, Internet Faith Learning Integration Presentations. In this particular iFlip, we'll take a look at some kind of practical things you might do in a science classroom to help students work on what might be an interesting, revealing, and perhaps exciting integrative project. And I'll give you an example using organic chemistry, but it's one I think that could be reproduced in a lot of different places throughout the natural sciences. Let me introduce this by thinking about something that isn't actually going on in the natural sciences, but rather in the humanities. In recent years, a discipline has formed in history called big history. And within this context, what happens is instead of looking at kind of individual small historical epochs and identifying key dates and key figures and key events, they take the big picture in. So when they tell the story of big history, they go all the way back to the Big Bang, and they talk about the things that happened in the first 10 to the minus 45th seconds of the existence of the universe, and what happened within the first second, and then within the first moments as things began to cool over the first 300,000 or 400,000 years. And they tell all of this story to help people understand how our little moment within human history fits within the great big history of the universe. It might be a thing that we do to make people feel just a little bit smaller about themselves and a little bit more respectful of the big universe, to realize there's a big story before we came and no doubt there'll be a story afterwards. I don't know what all the motivations are, but when you hear a person doing big history, you realize, wow, there's a lot more to think about with history than I once thought. So when I first heard about big history, it made me think about, it'd be interesting to do a similar thing that you might call big science. So for example, when I was an organic chemistry student, I remember taking a class, and one of the things that came up was certain reactions for fixing nitrogen. That is, taking normal diatomic nitrogen, and which is not useful in either animal or plant metabolism, turning it into ammonia or other nitrogen-containing compounds that are able to be metabolized. And that process isn't an easy one, and so it was very important when someone finally came up with a chemical reaction for fixing nitrogen. It's famously known as the Haber process, and it combines nitrogen and hydrogen and creates ammonia, and this has become a major source of fertilizer in the 20th century. Now, the interesting thing about this is when I studied in organic chemistry, it was an isolated reaction, didn't seem particularly interesting. I took it by faith that it was important, but I was never made to kind of wade in its importance. And I thought, wouldn't it be interesting is that part of an assignment I might have in an organic chemistry class was to do the big history of nitrogen fixation. And to stop and make a student think, what did it take for Haber to be able to come up with a process to fix nitrogen? What had to go before? And you realize, oh, well, they had to be able to at first isolate both nitrogen and hydrogen, because those are the two components they used in a purified form to create the ammonia. But you also had to have some kind of a vessel in which you could accomplish high pressures, because this is a reaction that will only take place at substantial pressures. But then you think, well, how did they even know that you could isolate gases? And how did they get pure nitrogen when we only meet it mixed with all kinds of other gases? And by the way, how did they know that a gas even exists? Because you don't really bump into gases. And you begin to trace these things back through a whole history of what did it take to know and find and identify nitrogen? What did it take to know and identify and find hydrogen? What happened? And before long, you're with Robert Boyle and Boyle's gas laws, and before that, you're probably dealing with the ancient Greeks and their own versions of atomic chemistry. It's a remarkable story when you begin to look backwards at all the things that had to happen in order for Haber to be able to come up with this process. Of course, when you do big science, you're not only looking backwards, but you're also looking forward, not just at what had to happen for Haber to have the insight that he had, but also what are the consequences of the insight that Haber had. And of course, in this case, part of the consequences that we suddenly had a radical increase in the amount of ammonia that we had available to us simply because we could synthesize it. And this ammonia became used for fertilizing and radically increasing the productivity of cultivated land. The effect that had was quadrupling the amount of harvest that came from the same acreage, and therefore we were able to feed vastly more people than we were before the Haber process was a possibility. That, of course, has had other effects, and some of those effects include things like acid rain. It may include actually bad dietary problems because of how easy it is to produce certain foods. So all of these complexities spin out of this single interesting tiny reaction that when I met it as an organic chemistry student wasn't really very interesting at all. My hope is, as we make these reactions more interesting and set in a great big story, we'll also find any number of connections to help a student do the integration of faith and learning on these topics. You begin to think about how it reflects backwards onto notions of science and human understanding, forward in terms of the implications of human society, the relief of poverty, with its social justice and other activities that come from the disproportionate distribution of food. All kinds of implications suddenly become connected to a relatively narrow chemical reaction. So thanks for joining us for this iFlip that takes just a little bit more in-depth look at what we might call big chemistry.